So with that, there you go, you're live.
Cool. Yeah. All right. Hey guys, how's it going? How's everyone? We're starting on time. This. Oh whoa, that's me. Yeah.
Oh my god.
You want to say hi later? Yeah, but hey guys, welcome back to RC3 week 11. We're gonna start on time today, which is great. I know, first time in like 10 weeks. It's great. Yeah, but you know, how's everyone doing? Just if everyone can. Oh, please hold.
I appreciate it.
It's not that.
But while this is happening, you can go to signin.rc3.club and fill out the sign-in form, as well as like a poll form, so we know how we're doing and sponsors know who's coming. But you can go to that really quick. Hi Ben, how's it going? How's everyone liking the cold weather?
My favorite.
Yeah, me too. Me too. Yeah, but you'd be from California and be cold here. Alright. Is anyone new this week? Guys, is anyone new this week? You're not new, Chris. You come every week. Alright, is anyone new this week? No? Cool, okay. Is anyone not on a CTF team yet and would like to be on one? Yeah? Who has a CTF team of four or less people currently? Alright, you guys should talk later. Cool, yeah. Otherwise, CTF, super important. Go do it. It's a great learning experience. You'll learn a lot. So next Saturday, we'll be in here from 11 to 3. We'll have food for you guys and music, and we'll be walking around helping out. It'll be like a long demo time, and you can do things with your team members. It'll be great. It'll be fun. Yeah. Otherwise, sign up for it. Definitely. What's up?
So what exactly is the format of that? Like, what does the whole thing look like?
So a capture the flag thing is kind of like, it's like a Jeopardy style board. So there's different topics. So like reversing, like exploitation, web, and all these things. And they have points from 100 to 500. And you want to do them, like they get points rate, like depending on how hard they are. And you do them, you get the flag, you get the points. Yeah, what's up? What?
Is this like one where it's just going to be up online for the entire weekend, or is it specifically in these labs, or?
It's going to be up on the entire weekend. You guys will be competing with people from around the world, but only RIT students can win prizes, so it'll be good. We spent a lot of money on prizes this year. A lot of money. Yeah, but any other questions, or?
How much money?
Like a lot. Like a lot. Like more money I made this month.
How much you make?
I don't make anything. Otherwise, a huge shout out to our sponsors, Grim, IOMaxis, HackerOne, SIG, and then Draper and Trello as our educational supporters. Yeah, but not a lot of things this week, so we're going to get right into it. Quick disclaimer, everything we teach is for educational purposes. Don't do bad things, or bad things happen to you. This week we're going to be doing intro to binary exploitation. We actually have Brad, the previous tech lead, who really likes this kind of stuff and is masochistic, but you know, whatever. But he's going to be talking to you guys about it.
Woo, Brad!
Hey.
All right.
Teach me how to play with the giggly bits.
That's literally the whole point of this presentation. So, I'm Brad. For those of you who have not had the pleasure of meeting, I am the previous tech lead for RC3. I do a lot of low-level software development, primarily C, x86 assembly on occasion, stuff like that, which is why I decided to start up the RC3 Reverse Engineering Group this year, which if you guys are interested in this sort of stuff, you should definitely come. We meet at Thursdays at 7 p.m. in 2590. That's basically at the end of the hallway over there. And we, for example, for projects, we are currently writing an assembly language for a game. It's a lot of fun. If you're interested in this stuff, definitely do it. I also am a person, so please talk to me. I love to help with stuff. I love talking about things, about my hobbies or your hobbies or anything, so don't be afraid to hit me up on Slack. I'm Brad Campbell on there. I don't have a weird username because it's hard for me to keep track of that, so I don't want to force you guys to. And without further ado, we're going to talk about exploitation. So what is exploitation? It's a very mysterious word for a lot of people, but what it is at the core is it's basically the leveraging of logic issues in code in order to get unintended consequences. So when you have an if statement that isn't written properly, when you have a loop that doesn't trigger properly, when you have an off by one error, these are all potential issues that can cause unintended consequences if that edge case gets triggered. So what you want to do is basically you want to go from point A to point C without hitting point B, or you want to create your own new point to hit. You don't want to go the way the developer directs you because that's boring. You want to go from user to admin without entering a password, essentially. And these are the whole core of exploitation. It revolves around known exploits, so stuff that are known to be vulnerable, which we're definitely going to be covering, and finding your own, which is where you basically are able to understand a piece of code that the developer wrote enough to develop your own bypass for some mechanism that they have implemented. And this is a very famous quote, not quote, but anecdote, I suppose. It's one of my favorites. It basically explains entirely what exploitation is. They say, get a loaf of bread. If they have eggs, get a dozen. But they don't specify get a dozen eggs or a dozen bread. So the person buys a dozen bread. And that's basically what exploitation is the taking advantage of ambiguous statements or logic flaws in order to trigger unintended consequences. So you need to start somewhere. You have to begin somewhere for anything you do. So the first step is to identify. You need to know what you're even looking at. You want to figure out where the code actually lies, what the code actually, from a high-level perspective, does. Is it an administration program? Is it a remote access program? Does it have shell functionality? Anything that might be useful to understanding what the core concept of the program is. Not even looking at the code of it, just figuring out what it's actually intended to do. And that gives you an idea of what the attack surface is going to be. Then you need to actually dig into what the code does. That's what the understand part is. You need to realize what they're actually doing at a level that a programmer would deal with. You need to know what they're looking for, what they expect, what they're intending to do, and then you need to go to the discovery phase where you actually see, this looks weird. Maybe I should try and fuck around with this a bit. And then you realize that there is some kind of bug, an off by one error perhaps, where they don't correctly check the bounds of something. And then once you have this discovery made, you can then start writing code that will trigger this bug in a reliable and stable manner. And so we're going to cover all this stuff today for some basic concepts which are really fun and really easy to do, but they are very real world stuff. There are bug bounties that pay out thousands of dollars to bugs like these. So the first process is identification. If you're not even looking in the right place, you're not going to find anything. You're not going to find a bug if your eyes are closed, basically. So you want to work smart. You don't want to reverse the entire assembly of the program. You want to know what it does and where you should be looking. And an easy way to do this is knowing vulnerable code and what it looks like. There's no easy way to do this. It's just practice, and memorization. Knowing what vulnerable functions are, knowing what some vulnerable code snippets look like, stuff like that. And having that dictionary of knowledge leads to much easier progress in exploitation. Obviously, you have to start somewhere, so you start off knowing nothing. I started off knowing none of this stuff, but you just kind of power through it. It takes time, but eventually you build up a dictionary, and you'll be able to open a program, and you'll be able to say, oh, this is potentially vulnerable, this is potentially vulnerable, and then you can start digging into the sections you need to look at. And that's the whole point of identification. Once you have and have a goal. You need to know what you want. Don't just start. You have every right to take apart a program and just figure out what it does, but if you're trying to exploit a program specifically, you need to have a goal. Do you want to read a file? Do you want to get a shell? Do you want to set a variable like isAdmin to true? You need to know what you want in order to know where you're going to look. Otherwise, you're just going to be kind of wandering around with a hammer hitting random things hoping they break, which works all the time. That's called fuzzing. However, we're not really covering fuzzing for this. This is more directed. So, once you know what you want to look at, you want to understand what you're looking at. So you need to reverse engineer the parts of the code that look like they're important. The variables, the control flow, what it's executing, strings that are presented, what it intends to do, what's the purpose of it. You want to know what the overall purpose is. And this is important because you don't want to be reversing every single assembly line unless it actually matters. You want to go from a high-level understanding to a low-level understanding where it matters. Otherwise, you are going to be wasting a lot of time and energy understanding irrelevant parts of code. And there's a lot of methods to gain more understanding about this, like reading the external functions that are linked, seeing what kind of loops are available. Does the actual code deal with input that you can control? Are there side effects to stuff you enter? These are all very important in the exploitation process, and they lead to a bigger picture on how the program actually operates and what the consequences of changing input are. And you only want to be looking at input. If you don't have control over a piece of code, it's generally going to be very difficult or impossible to trigger an exploit in it. You're looking for stuff where you are able to affect the control flow, the variables that are present in it, just some form of the code. And those are generally the most important parts to look at, like the main function, some function that's called a bunch of times. If it's just some like dead code piece that never gets called or like you have absolutely no control over, it's very seldom going to be useful to you. That's not to say it will never be useful to you, but it is generally going to be more fruitful to look elsewhere. And this is where your reversing leak is going to come in handy. This is where reading x86 assembly is going to be useful, because not every program writer is going to give you access to their source code. They don't want you reverse engineering their program most of the time, so they're going to not provide you the source code to it. You're going to have to figure out what the source code is from the assembly, and that is a difficult process. It's time consuming, but it's very rewarding and fruitful when you are able to take things apart that were not intended to be taken apart. If that makes you happy, this is a very fun field to get into. I can personally attest to that. So then you go into the discovery process, like what do you control? So once you figure out what you can control, you can figure out what the side effects of that are, and if there's anything that is potentially vulnerable. Like you can say, all right, this is a loop here, and this loop gets called a bunch, and it looks like there's like a weird off by one error when I'm debugging it, when I'm reversing it. You need to figure out, is there anything that would possibly affect the user input? Does it get transformed in any way? For example, if you're sending in an HTTP header to a known vulnerable web server, does it get processed in any way that would potentially hinder the exploitation phase, that would mangle the string you gave it? Like for example, if you send it a base64 string and if base64 decodes it, that's obviously a stage that would change it. So you would need to work around those formats in order to get your code to trigger the parts you want. And then that brings us to the most fun part, breaking it. I love that little bug, dude. He's just so adorable. But you want to actually figure out what inputs will trigger the desired effect, or in this case, the programmer's undesired effect. You want something that is reliably able to basically get this unintended feature to happen, and the unintended consequence is, of course, what I said earlier, where you need to have a goal. You need to know what you want this to come to. And we're going to cover some base work for this. This is just a generalized methodology that I always follow when I'm taking apart a program. So we're gonna. So in the following slides, I'm actually going to tell you some common vulnerabilities, some common bugs, and how to exploit them. However, I very much want to stress that copying and pasting this sort of code will rarely work. If you just go on ExploitDB, copy and paste stuff, that is not really going to be super reliable for stuff like this, because you need to have a fundamental understanding of what the bug is and what the exploit does and how to make it work for you. And also, ExploitDB is not really vulnerabilities. Those are exploits. We're talking about classes of entire vulnerabilities here, not just single exploits for a piece of software. Which brings us to the first part, the known vulnerabilities that you need to have a dictionary of in order to facilitate rapid disassembly and taking apart of the logic of the program. Knowing where the vulnerabilities are is your greatest asset, because this is going to lead to you knowing exactly where to look. If you see vulnerable functions being called in code, you know you can go straight there and you can backtrace where the input's coming from and see if you can control that in any way. And if you can control that, there's a chance that you have access to options that the developer did not intend. And as I said, this is not ExploitDB or Metasploit. This is developing our own. This is what they do to develop those exploits. They have a process. This is my process I'm showing you guys, and it's just, you need to understand the underlying exploit in order to know what the class of exploit does to make your own. And it's very fun to do that. As you guys will see, you're going to be getting remote code execution on a lot of stuff. You're going to be tricking scripts and programs into doing things and revealing things that they wouldn't normally want to reveal. So for example, Python. Yes, Python is vulnerable to things. Exec and Eval primarily, what these do is they are functions, and what they do is they take user input and they evaluate it. And what this means is if I provide eval a string that says print hello, it will literally run print hello as a Python program. Now, obviously, this is dangerous. This is literally running Python code from an unsecure source on a environment that you don't want them to have access to. Like, for example, this calculator I provide right there, if you have, for example, remote access to something similar, you can provide code to that. Instead of just doing 1 plus 2, where it will evaluate that and return 3, you can provide file open, you can like open a file and read a file, and it will return the file results. This is obviously bad, and we're going to show some exploit stuff. It's really easy to do these sorts of things because it's just plain text, and that's why I like them so much. And they're also very prevalent. I've seen bug bounties worth thousands of dollars that get paid out because of stuff like this, because some coder messed up and they were like, oh, I'm just going to evaluate this post parameter from this web server because it's like a math statement and I'm too lazy to write a calculator, and then boom, you have remote code execution. Next up are pickles. Python pickles are really interesting. They are called data serialization. For those of you who are not aware, serialization is the process of taking an object or basically some kind of memory object in a language, then you serialize it into a stream of bytes, and this stream of bytes can be saved on the disk, can be sent over the network, you can do whatever you want, you can speak it in Babylonian, I don't care, but the purpose of it is you take those bytes and you then put them through the deserializer, which converts that stream of bytes into an object in the program's memory. So you get an exact copy of the object from one computer to the other, basically. It's really useful for saving state. Some games will do this to save like save state objects or configs or whatnot. However, in the case of Pickle, as you can see at the bottom there, if you guys can read it, it says Pickle is not secure against erroneous or maliciously crafted input. Never unpickle data received from an untrusted source. And this is because in order for Pickle to properly put the object into memory, you can define code that gets executed to format it properly. So moving on to C, which is what a lot of people think of when they're thinking of exploitation. C, a lot of exploits are known as memory corruption, whatnot. Basically what they're doing is they're exploiting the way that memory is handled at the machine level, the way what C compiles into. It compiles into machine code, and it exploits the way it handles this machine code. So for example, strcopy and getS are two very well-known functions that are vulnerable to what's known as a buffer overflow. And what a buffer overflow is imagine I take a glass of water, which is my destination buffer, or so, it's more like an empty glass, I suppose. So suppose I have a destination buffer of an empty glass, and I have a huge pitcher of water, which is my source. I just start pouring it in. Eventually, it's going to flow out of the glass, and that stuff has to go somewhere. And it's going to overflow into other parts of your code. And this is going to overwrite local variables, control registers, data, like all kinds of things. You do not want it to break. A lot of times this will cause a segmentation fault. However, in the case of a buffer overflow, sometimes you can control this segmentation fault to execute code that you don't intend to execute. You can actually control the next machine instruction that is going to execute. Printf is also another vulnerable function in C. And this is interesting because this will bypass a lot of protection mechanisms, because you can just read directly off the stack. You're literally telling Printf to read off the stack. It's called a format string attack, and we'll cover how to exploit that shortly, but basically it allows you to just read and write to local stack memory. And also, anything that writes to a buffer has the potential for this stuff. If a coder doesn't properly validate buffer offsets or buffer ends or anything, their own code, if they write a for loop, just because they're not calling strcopy, that doesn't mean they won't accidentally write a function that will just trash a buffer and just go off into infinity if you provided a very long user input. And that's where actually understanding the assembly code that's being written is important.
Grab a drink of water.
So is everyone with me so far? Is everything I'm saying making sense? Does anyone have any questions at all? I don't want anyone to be left in the dust. All right. So this is going to bring us to another one, and this one is typically language agnostic. It's code injection. You guys might have covered this before at RC3, but this is prevalent in every single language. This is similar to the Python eval, but what this typically does is you're calling shell subsystem commands. So for example, you're calling a bash command, you're calling a batch command on the back end. So for example, if you have a program that is automating the addition of firewall rules, and you're just calling IP tables on the back end, you can potentially insert code into a firewall rule if you have malicious use of this program. You can potentially insert code into the firewall rule that will trigger, for example, rmrf/toTrigger. And these occur in all languages. C has the system function. Python has subprocess popen, especially if you call with shell equals true. That's very bad. os.system is the exact same thing as subprocess popen shell equals true, but it doesn't. It's semantics. But all languages have something like this. I believe PHP has a system as well. A lot of stuff will have access to the underlying shell because the underlying shell accesses operating system internals and allows you to do very useful and very powerful things, but it also needs to be handled very responsibly. And it's actually the OWASP #1 vulnerability because of how easy they are to trigger. If they exist, you can trigger them with plain text usually. They're super simple to exploit, and they have devastating consequences. So now we're going to actually talk about exploiting these vulnerabilities and how to make them do your bidding, which is super fun. I love this sort of stuff. So we're going to talk about Python first because Python is very easy to understand and see where it goes bad. Eval and Exec, as I explained, basically run a string as raw Python. This is obviously pretty terrible, and you can see where the problem is I can just tell your server some Python like, hey, I want you to run the calculation 1 + 2 and open this file and return the results to me that you don't want me seeing, like Etsy password or something. I now have access to all your usernames and can brute force stuff. For example, I have a Python snippet right there that opens stuff. However, a lot of times these are going to be one-line restricted. You're only going to have one line to execute this stuff. If you don't have a library you need, you might be out of luck for stuff, except for the fact of this second example. It's what Python calls a runtime import statement. So what this allows you to do is it's a directive that allows you to import a function at runtime based on a string, and then you can directly access the function methods, or sorry, the library functions that way. So in this example, it's a one-liner. Instead of having to do import os, new line, os.system, evil command, that would break in the eval program that I had running earlier because I constricted it to one line. So this allows you to do much more with much less, and it's very useful and comes in handy a lot if you're ever doing a CTF challenge involving a Python exploit. Pickle Rick. So Python Pickle, as I said, serialization is very powerful, but it's also very dangerous. The reduce method on a pickle object defines a function that will format the code in memory and then objects for it as a tuple. Yes, the comma is not a typo. Doing so defines it as a tuple. It's just a semantic language thing. But basically, this reduce function gets called. It will literally run the function with the arguments you provide. So in this case, if I serialize this and I pass it to a function that's expecting any serialization, if it can be expecting like a crayon object, but it's going to have to deserialize it before it knows that it's not the right thing, and by then it's too late, you lose. So this is a simple exploit that will basically run the command ls. You can obviously substitute any command in there. You can substitute any function, any library. The caveat is that the library will need to be imported by the code, and that's where understanding Python is going to come in handy. As I said, you can copy and paste this all day, but if they don't have OS imported in the vulnerable code, it will fail. You need to understand what the vulnerability does, and you need to understand how to trigger it. So understanding the vulnerability in that case would be knowing what libraries it's actually importing, and then going through the process of understanding how to trigger something that is unintended with that code. So another one we're going to talk about, and possibly one of my favorites, is the C Printf vulnerability. These are the format strings that I mentioned that are so dangerous. So if we can control the format, we can control the stack. This is due to what's called a variadic function. So a variadic function in C is a function that takes an unknown number of arguments. So this is important because, as you know, you can pass a variable number of arguments to printf. And what this means is that at compile time, the function doesn't know how many variables are going to be on the stack. It cannot really format the stack saying that, oh, there's only so much space for variables. What happens is, in these variadic functions, you have a condition and you have a retrieval stage. So the condition stage basically says, are there items on the stack that I need to retrieve? So for example, if I have a sum function defined that would take an int number of items, and it would take just a list of integers. So the number of items would be the condition here, so it would be while there are more than 0 items left on the stack, and then it goes to retrieval phase. Pop an item off of the stack, and then it will operate on that. The way Printf does this is by iterating over the string that is provided as the first argument, and if it receives a valid format string, it will pop an item off of the stack. So in this case, in the first example, it will print the variable name because the variable name is put on top of the stack. So it will pop off, once it reaches the %s, it will pop off the item on the stack, and it will interpret that in the way that %s interprets it. In this case, it will dereference it as a string, and it will print it out. However, if I'm calling printf with multiple %s's, but no arguments or too little arguments, it's not going to crash, or it may crash, but it's not going to directly say, hey, there's no data for me. It doesn't know that there's no data for it. So it's going to retrieve the first item on the stack, and then the second, and the third, and the fourth, until it's done. So what this will end up leading to is information leakage. Have you guys ever stored usernames, passwords in memory, right? Like, I'm sure we've all done that in a CS class or two. Sometimes it has to happen. If you've ever stored sensitive data in memory, like for example, a web server might be storing a list of users connected, or their connection information. Any sort of sensitive information will likely be reachable from this, because you can just keep popping back through the stack, and you can access these sensitive pieces of information that you were not intended to access. And this is very useful because you can then cause significant damage. This is definitely an exploit, because while you may not be executing code directly right now, you're still reading data that shouldn't be read. Like one example is that a lot of times environment variables will store API keys, usernames and passwords, connection information. Like if you've ever stored your GitHub API key in your programming environment, if you have a C function that is making use of your programming environment and it has this vulnerability, that key can be accessed by code. Because the C environment in certain cases is stored on the stack, and you can just pop back and just retrieve the items. You can enumerate your entire environment variable collection. One thing that's important to know with printfs is a lot of times %s will cause a seg fault, as I put in the footnote. So this is because it's trying to dereference a null string. If you ever try to do printf %s and then provide the argument 0, you'll see why, because that's essentially what's going to be happening. Or it might be referencing some other address space that's not valid. In that case, you'll just build a format string that, for example, in the second example right there, if, for example, the third %s causes a seg fault, I can just simply replace that with something that doesn't pop an item off the stack and dereference it. For example, I usually use a %x. That just reads it as a raw hex value. It'll say 0, and then you move on with your life. So if in, for example, the demo you are getting stuff like that, that's usually what's going to be happening. You're just going to have to replace some %s's with %x and keep going on building your format string until you get to the juicy data. Also, there's a neat thing called direct parameter access. It's not part of C specifically, but it's part of some of the GNU specifications, I believe. What it means is instead of having to say %s 4 times, I can just do %for $s, and it will print the 4th item on the stack as a string. So this is awesome because instead of having to build a 400 character long format string vulnerability, which I've had to do, like they can get ridiculously long, you can just do %400$n. Sorry, $s. $n, I don't know if I have a slide on that. No, I don't. Okay. $n is, or %n. %n is a really cool format specifier. What it essentially says is count the number of characters that I have printed out and write them to an integer pointer. That's bad. We literally now have the ability to print out a number of characters and then write that to a location of our choice. Before a lot of exploit mitigation techniques came up, you could use this to execute arbitrary code, because you could just dump your shell code onto the format string and then overwrite a pointer and say, oh, hey, execute my shell code. It's a bit more difficult now, but you can still override local variables. For example, in the example, when I said you have an isAdmin Boolean, right? You want to identify if the user is an administrator or not, and you check that variable at some point. But if you can set that to 1 with %n by writing out a character and then doing %n on that integer pointer, you will now be considered an admin by the server. And that's why Printf is so fun. Another one are the buffer overflows. So these are very common. These are very famous. This is like the de facto, like, oh, this is what I see as exploitable stuff. And they're very cool as well. So, as I said, they are built around the idea of you are putting more data into a container than the container can contain. And typically in a memory safe language like Java or something, it's going to ignore it, or it's going to throw an exception, say an array out of bounds error. In C, we have no such thing, and it's just going to happily write data to the 100th index of a 10-byte long array. It doesn't care. It will continue to do that happily and merrily until it crashes. And we can exploit this. If you guys, in Reverse Engineering Week, you may have noticed that there are the call instructions in x86. And what this does is this pushes what's known as the return value onto the stack. And what this does is it's a backup of what's called the EIP. And the EIP is the instruction pointer. This is a register that says, this is the next machine code we are going to execute. When you return from a function, you are restoring this old value. So you are going to return to your old spot. The EIP will point to the next instruction that was going to execute after the function got called. If you can overwrite this by overflowing a buffer past its bounds and controlling that value, you can now tell the program where you want it to execute the next instruction from. Before common exploit mitigation techniques, this would lead to trivial code execution, because essentially you would be able to put executable code into your buffer, and then you can point the EIP to that buffer. That's very obviously not good, because you are providing it any sort of code you want to run. If you can build it in assembly, you would be able to put it into that buffer and have the server execute it. So this is one of the most dramatic of security vulnerabilities. We're going to cover some exploit mitigation techniques at the end of this, which will explain why these are much more difficult nowadays. However, they are still very prevalent in environments that aren't entirely secured. So the way to find these is typically via a known vulnerable function, strcopy, getS. A lot of times these will be compiled out, so sometimes you'll have to find manual code. But what's happening is you have a buffer for a username, right? So this username buffer is, let's say, 16 bytes long. You read a username from the user input, and you put it into that username buffer. That seems like logical enough code, right? That's something that we've all written. I've written that. And what happens is, if you don't if you don't length check the source array, basically, if you don't check the length of the user input, I can input a 400 character username. And this would get happily written into the 16-byte space, and it would just trash the rest of the stack variables that are stored. And if you properly format the buffer in such a way that it contains shellcode and a valid instruction pointer, then you can basically insert whatever you want in there. And that's why these are very powerful. They can also be used to set user as admin true. Like how I said, Printf can set stack variables. Since this trashes the stack, if I have a 16-byte username on the stack and I also have a 4-byte integer saying user is admin, if I send 16 bytes and then I send a couple ones, that will overwrite the user is admin to a true value, and it will assign you as an admin on the code, theoretically, if this is exploitable. So this is pretty bad. Like, you can get code execution, you can modify the flow of code without actually passing through a correct stage. And then code injection. So these rely specifically on knowledge of the underlying shell and the command that's getting called. So for example, in Bash, if you have a program that's taking your user input and calling system, for example, if it's returning the the directories in your root directory, it will run ls, or in any directory you choose, I suppose. So it would run ls and then it would put in your user input. There's nothing stopping you from entering ;rm-rf/, which would delete your hard drive, and it's very bad. And these are very difficult to protect against because you have to apply what's called sanitization. Sanitization is the process of filtering the characters in user input in order to prevent these dangerous characters. It would be something like escaping the semicolon so that way it doesn't actually trigger a new command in Bash. It would be escaping $ parenthesis to prevent subshells. Same thing with the backtick mark. That also executes subshells. It's this is a very difficult problem to solve, however, because you can't control all of the edge cases usually. A lot of times, there will be a case where someone can run something you did not expect in your sanitizer, or some new feature gets pushed out that you haven't updated your sanitizer for yet, and now you have code execution because of this. It's very difficult to protect against it. It's very useful to have stuff like this. However, you need to be very aware if you're writing code that does this, how dangerous it actually is and how easy it can be to exploit if you don't properly handle the input. So now that we've talked about all these exploits, we're going to talk about things people have done and developed to prevent them from happening. The first one is called DEP, Data Execution Prevention. And what this is it assigns permissions to memory pages. Just like Linux permissions, read, write, and execute, memory pages will now be read, write, and execute. What will happen is your compiler, when it builds your program, will say, all right, this is executable code, so we don't want people writing to it. So it'll be read and execute. Or you'll have variables, for example, your username. You don't want your username to execute, but you want to be able to read and write it. So we'll mark it as read, write, but not execute. And what happens here is that you will, if you attempt to execute code that is not marked as executable, for example, if you try the buffer overflow exploit I mentioned, where you shove shellcode into a username and then jump to that username, in this case it will be marked as read-write. Therefore, when you try and execute that, your processor would throw an exception. You've commonly seen this as segfault. It'll say, hey, this is not valid, I can't execute this memory address. It'll crash the program. So this is one of the techniques that have been developed in order to mitigate the ease of exploitation. Some of these are there are techniques to bypass these, but what this does is it raises the bar of exploitation. It just makes it that much harder, that much more difficult to actually get your exploit to work. Another one is ASLR. So ASLR, what it does is it randomizes the address space of your program. That is why it's called address space layout randomization. What this does is, before ASLR, when you ran a program, your main function would always be loaded at the same address. Like, for example, it would be loaded at hex 4000 every single time. And what this allows you to do is it allows you to interact with memory via direct offsets. So you can specify a hard-coded memory address. For example, if I want to trick, for example, if I want to jump to the system function to execute an arbitrary command, I will know exactly where that function is every time this program runs. I can just hard-code a jump to that, and I win. What ASLR does is it means main might load at hex 4000, 5000, 5029. It doesn't matter. Obviously, it won't load at 29 because it's odd, but that's semantics. What I'm trying to get at is that you will not be able to hard code addresses in anymore because they will be different each time. You end up having to. I'm blanking on the technique to get through it, but it dramatically increases the difficulty of exploitation because now you cannot hard code these memory addresses. You cannot just jump to shellcode and execute it either, and they are very powerful combined. And however, this is also one thing that hasn't been prevented yet. We've prevented executing of stuff we can write to. We've also prevented from being able to easily jump to executable code. One of the exploits I haven't mentioned, which is where you can write to local variables from a buffer, hasn't been protected against yet. And this is what the next exploit prevention technique is. It's called the stack canary, which are adorable. I've never really looked up a picture of them, but they are so cute. And what it does is versus dep, whereas dep prevents you from executing code, a buffer overflow can still trash stack variables. You can still overwrite the user as admin variable. Stack canaries work, they typically work in conjunction with stack hardening, where stack hardening will allocate the memory for your functions such that buffers are at the very top, and they will put all your other variables below that. So that way when you overflow it, you are overflowing directly into memory that is not part of your function. And this works in conjunction with stack canaries. And what those do is they put a canary at the top of the stack. And what this canary is it's a randomly generated value. And this randomly generated value is checked at the end of the function. or other points in between. I don't know if it puts it in between. However, I do know at the end of the function it will call it before it jumps to the EIP. And what will happen is, if the randomly generated value is changed, it will compare it to another saved value. And if they differ, it will kill the program on the spot. It will say, this should not ever happen. Someone is trying to, it will print out a message saying stack smashing is detected, and it will immediately kill the program on the spot. You will get no farther. It will not jump to your code. It will not do anything. And the origin of this is really cool. Coal miners would used to take canaries into the mines with them, and the canaries would chirp the entire time. And they are very sensitive to toxic gases, so if they stopped chirping, the miners knew that toxic gases were building up, and they would leave, which is essentially what this is doing. It's really cool, the correlation between it. I just like including that. It's a really neat piece of trivia. And that really brings us to the end of this. That is the crux of basic exploitation in Python and C. Those are the core fundamentals that I feel like are very important. There's very much more that could be gone into, but each of these individual topics can be a 1 hour long presentation at least. If this is something that interests you, feel free to message any one of us. We're more than happy to give out resources. It's a lot of fun. If you enjoy this sort of stuff, it's a very fulfilling thing to do, being able to take apart a program and exploit the logic in it. Does anyone have any questions about something I talked about, something I didn't understand? I will answer anything at all that you guys don't understand. All right. It seems like you guys all got it, so I think that's demo time then.
Yeah.
Awesome.
Cool. Just one thing. Yeah. What's up?
What's the flag for the local flag?
I was gonna say that. Yeah. But also before that, so me, Sean Newman, and the two new juniors, Simon and Zach, we all went to Hack PSU last weekend and gave like a series of talks. It was basically like weeks 1, 3, and like 4, pretty much. So we went there. It was great. We got our name out, and they gave us like a stack of domains, like domain coupons. So if anyone wants like a free .com domain, come see us or make a line. I don't know how many of you guys are interested, but also we have like a large number of pens for some reason. But
Somebody actually just dropped a ton of pens on it.
Yeah.
You got pens on.
what's up?
I need a pen.
I only have a couple.
I don't have a pen. I don't want to go in.
Alright, I'm just gonna start this.
If you want a thing,
Embrace your inner Britishness and form a queue right here.
Cute.
Here, I'll let you deal with this too.
Newman has the pens too.
Oh God. I'm hoping we're gonna have enough for everybody. It looks like we will. I gotta count first. So.
Yeah.
How's everybody doing? Actually,
Good. How are
talking while you count's a bad idea.
Yeah.
How many are you giving?
Just seeing how many they have in total.
I don't know. I mean, like, you want half?
Hey.
All right, we're gonna do this like elementary school and count off from the front to the back to see how many people.
1,
2,
3, 4, 5, 6,
7,
8, 9, 10, 11, 12.
15? Cool. We're gonna do one for everybody, and if you want a pen, they're all right. There's only 7 of them though.
I'm good.
All right. Cool.
Thank you.
Pen?
No thanks.
All right. Pen?
Yeah.
All right. 6 pens.
Yeah.
Pen? Okay. 5. Yeah. Okay. 4. Pen? 3. Pen?
Sure.
2.
Sure.
1. Pen?
Yes, please.
Last man with the pen.
I'm upset.
I'm sorry.
Thanks.
Economic problems. Thanks,
Yeah.
John. You're allowed.
They also expire June
Base one,
30th,
no
so make sure you use them before, or we'll bring more. But wait, is that it? We didn't run out.
No, we still have 15 left.
Ah, fucking
I could have given 2 to each people, but I don't want to give away all right now.
Give it away more at the CTF too. All right, that's the sign-in flag.
Hey, if you weren't listening to Sean, they expired June 30th, 2018. So make sure to register it before then.
Yeah, but that's the signing flag. Get your 10 points. Otherwise, Ivor will walk around, help you guys out.
Any more of the demean commands?
It's just, it's never worked out like that.
What challenges there are no flags? No flags? Oh, I guess I didn't see that. Since I didn't have, I don't know if
I got an 80.
Yeah, I got our class average he sent an email about that. Apparently there were several 100s.
Not that good for Ollie.
You realize after the last test I need to throw us a bone.
I think he sent that to everybody.
Yeah, it's the same one. Maybe that's all the classes.
Yeah, it's a pretty good average.
That's a really good average. It's going to last from 68. It's not up just a bit.
It's like 20 points.
Week 11. Back to the website.
It's not working.
We're all trying to sign at the same time.
Invalid security fund.
Oh wow. There's a reason I brought my mouse.
I'm not doing that.
You're good. Just making it known.
Wait, can you see me typing? Oh, there we go.
Week 11.
Joel, what are the ports? Mm-hmm. Through what? Okay.
Hey, PM.
Just DM Simon.
DM me.
Some of you really triggered.
Joel, just PM me on Slack.
Which because you can't really get banned. That's how we Overwatch.
They have to net cap for that. What's up?
You guys want to make an announcement that the Grim challenges are up?
Oh, so the Grim challenges are up, by the way. The Grim Hacks thing for November, that's up. It's very blue teamy.
It's very Windows oriented.
It's Windows.
It's very Windows.
PowerShell.
It's a lot of.
Get smallest child. I think that's a command. Is get smallest children child member. Is it? Fuck. I got new.
Yeah, no, I saw. I know.
Oh,
I don't
Slack.
want to eat more donuts.
I don't want him to see.
Probably a good idea.
Yeah, I don't want him to see my Slack.
I don't know my group password.
1337 through.
Yeah,
1341.
Creates a conflict, so only register to say yes. Unless I roll that first, and then file.
should probably make backups for my SIF.
Well, yeah, it's just the whole.
What you doing?
So, especially now we have
Alright, there you go.
I didn't expect it to break.
HTTP, week 11. Netcat. Connect over Netcat. What? That sounds like weak sauce. I'll use burp. Use burp. I like to be able to replay my packets. All the packets.
Dude, I'm trying to solve this PCAP.
Which PCAP?
Hang on. Let me fix some things here. We're gonna extend the displays.
What'd you break?
It's all DOD.
That way I can do shit over here and they can still see that.
Fuck that shit.
PCAP. I'm trying to solve
There's
this.
only 4 packets.
No, there's not. Fuck off.
What's your problem? Alright, so what's the challenge? What are you trying to find?
I don't know. That's the problem.
What do you mean you don't know how?
So far, we've been collecting memes.
What?
Oh, wait,
We should probably
what's-
stop the stream.
What's the? Was there a clue? Was there?
Oh yeah. Here.
Give me the.
Can we stop? Newman! Can we stop the stream?